See, the present problem involves the conservation of energy in rotational mechanics. In the problem, we have a solid cylinder, a pulley, and a block. A string is passing over the pulley, and one end of the string is attached to the block, and another end is fixed at the center of the solid cylinder by a yoke. Yoke, you can think like a wooden clip or wooden frame. So the string is attached at the center of the solid cylinder by yoke, so that when the string is pulled, the solid cylinder will rotate. And it is given that initially the system is at rest, the string is not slipping anywhere, the cylinder is rolling without slipping on the tabletop, and the axles are frictionless. So initially the system is at rest. So if you see, when the system is released, what will be the different types of motion associated with different objects? When the system will be released, the cylinder will undergo rolling. The pulley will perform pure rotation, so it will perform the rotational motion, and the block will undergo translation, right? So block will be associated with only translational kinetic energy. Pulley will be associated with the rotational kinetic energy, while the kinetic energy for the cylinder will be both the rotational as well as the translational. Suppose we are considering a time t after release, okay? Let us consider the time t after release. Let us consider the situation at time t. Now, since the string is not slipping, so we know the fundamentals. In that case, the points of contact would have the same linear speed. So see, if you see this segment of the string, if the center of the cylinder has a linear speed v, this point will also have a linear speed v, and so v will also be the linear speed of this point and also for the block. So we can say the center of the cylinder and the block will have the same linear speed. Say at a time t, the cylinder has an angular speed omega 1, the pulley has an angular speed omega 2. Already v you have labeled for the block. Now if a is the constant acceleration of the block, a is what? The acceleration of block, and block is started from rest. So if you apply the equation of motion, so you'll get v is equal to what? U plus at, and u will be 0 because the block has started from rest. So v comes to be what? At. Now, since this point will also have the same linear speed v as the block because the string is not slipping, so we can write v is equal to what? R omega 2. V is equal to, what is the radius r, and angular speed is omega 2, on the basis that string is not slipping. And since the cylinder is in pure rolling, so you can apply the concept of pure rolling, which says that center of mass speed is r omega. So for the pure rolling of cylinder, the center of mass has a speed v, radius is 2r, omega is omega 1. So we'll grab this equation, v is equal to 2r omega 1. Okay, so we have these different equations relating v, r, omega 1, omega 2. Now we want to apply the conservation of energy, and before applying the conservation of energy, we have to define a system. So say I'm taking the system as the planet, the cylinder, the pulley, as well as the descending block. So I'm taking the system as all the objects including the planet, and since planet is taken within the system, the gravitational force will play its role in the gravitational potential energy and not in the external work. And since friction in rolling, even if there is friction, it would be static in nature. So in rolling, static friction will do no work. So we can say the external work will be 0 Now let us find the different changes in the corresponding energies. So change in the gravitational potential energy would be what? Say the block comes down in a time t, it comes down by height h. So it would be minus mgh, and h you can find by the equation s is equal to ut plus half at square. So for the block, let us put s as h, u would be 0, block is starting from rest, half at square, right? So in place of h, what I can put? Minus mg at square by 2. So this is your change in the gravitational potential energy. This is one change in energy, gravitational potential energy. Now, what is the change in the kinetic energy? So let us find the final kinetic energy. The energy associated with the block would be simply the translational one, half m v square. The energy associated with pulley, as we have seen, is simply the rotational energy, half moment of inertia of the pulley, angular speed, that is how much? Omega 2 square. Now, the energy associated with the cylinder, it is in rolling. So, rolling energy will include both the kinetic, that is half mass of the cylinder, center of mass speed, v square, plus half I, say I1, and I'm giving pulley as I2 because they may have different I's. Say it has a moment of inertia I2, and say it has a moment of inertia I1. So I1 omega 1 square. Okay, this is the final kinetic energy. And the initial kinetic energy would be 0. System has been released from rest. So delta K will simply be what? The final kinetic energy. So it will come to be half m v square plus half. What is the moment of inertia of the pulley? So pulley has to be taken as a disk of mass m and radius r. So it will have a moment of inertia about the central axis as mr square by 2. And what is your omega 2? You can use equation number 2, v by r. Okay, plus half mv square plus half. Now I1 is the moment of inertia of the solid cylinder about the central axis. So the radius of the cylinder is what? 2r, and the mass is m. So it will be m radius square by 2. Now what is your omega 1? It is v by 2r. v by 2r square. Okay, so you will get the change in the kinetic energy is, you can see this r square will get cancelled away. So we'll get half mv square plus half m r square will get cancelled away. V square by 2 square, sorry, 2, not a square. Square is in this one, plus half mv square plus half m. Now 2r square will get cancelled away by 2. So delta K will come to be what? mv square. Now it will be half plus 1 by 4 plus 1 by 2. That is again plus 1 by 4. So we'll get delta K as how much? We'll get 2 times of 4. That is 1 by 2, 1 by 2, 1 plus 2 by 4. So we'll get 3 by 2 mb square. This comes to be the change in the kinetic energy. Okay, so we have done with the change in different form of energy. We got delta K, we got delta U. External work will be 0. Now put what? The conservation of energy equation. Delta U plus delta K is work done by the external agent. So we'll get minus delta U came to be minus mg at square by 2 minus mg at square by 2 plus 3 mv square by 2 will be equal to what? 0. Now 2 will get cancelled away, m got cancelled away, so therefore you'll get 3v square is what? GAT square. Now can we get v in terms of a? So v is basically the speed of the block when it has traveled a time t with initial velocity 0. So you can write v is equal to 80. Already, I guess we have written in equation 1. Yeah, v is equal to 80. Already we have seen that was equation 1. So I'll get 380 square is what? GAT square. So I'll get 3a square t square is GAT square. It will get cancelled away. So what will be a? One a will get cancelled away. So a will come to be g by 3, and that is the final answer to the problem. The block would be accelerating downwards at g by 3. So I've seen how we did the problem using the conservation of energy approach.